Hey guys, I wanted to take a second and make a little video showing you how to solve problem number 9 on your chapter 7 test. Now, if you look in the upper left hand corner, you can see this is for version 1. And if you're a version 2 person, before you click away, I still think it'd be really beneficial if you watch this. It's going to be pretty much the exact same process, just your numbers are going to be a little bit different. If at the end of the video you're sitting there going, I still don't get it. I've got version 2 and I don't see where my numbers are different. I can look at that with you one-on-one. But please, whether you struggled with problem number 9, the chicken wire problem with Mrs. Paulson in version 1 or version 2, this video should help you understand how to solve it. What I'm going to be doing is I'm going to walk through each step of the process, how my brain kind of works through it. This does not mean you can't think about it maybe a little bit differently, but I want to give those of you who struggled maybe a process to follow. So looking at the problem, we see that Mrs. Paulson bought chicken wire to surround the perimeter of her rectangular garden. Off the bat, you know me, I love pictures, so I'm going to draw just a little rectangle over here to kind of give myself a visual. Okay, it's a rectangular garden. I also know that it's the perimeter, right? We're not finding the area of the garden. So we're not going to be doing what's running through my head formula-wise. I'm not doing base times height or length times width. That's the area of a rectangle. Rather, we want the perimeter. Perimeter, I think, add up all the sides. She's restricted to no more than 30 feet in width, okay? She wants to use at most 180 feet of chicken wire. So we got a couple restrictions you can see in blue and red. 30 feet in width, 180 feet of chicken wire. We're told X is going to be the length and Y is the width. So that's kind of our info, but what do we actually need to do? Well, part A says we need to write a system of inequalities to describe the situation. Part B, we need to graph the inequalities and list at least 3 several solutions. Well, I'm not going to worry about part B right now because I know that in order to graph inequalities and write solutions, I got to first come up with them. So part A's got to come before part B. So let's focus on part A. Write a system of inequalities to describe the situation. Well, the way we come up with a system of inequalities is just like how we'd handle word problems with equations. We're going to look at the criteria, look at the key info, and come up with some equations to talk about it. So let's look back to the prompt. She bought chicken wire to surround the perimeter of a rectangular garden, no more than 30 feet in width. Let's focus on that. No more than 30 feet in width. Well, that screams out to me that we've got this width and we don't know it, right? We don't know the width. They don't tell us anywhere in here her garden is 47 feet wide. No, they just give us this general criteria. So no more than 30 feet in width. Well, I don't know the width, so I'm going to give it a variable, W. Well, wait a minute. Actually, they tell us, I got to read a little bit more carefully. They already give us a variable for width. They tell me Y is going to be my width. So we'll have Y equals width. And they tell us that it can be no more than 30 feet. So Y and 30, and the open side of that inequality is going to face the 30, no more than 30. Remember, open side faces what's bigger with inequalities. But the phrase no more than does mean I could equal 30, right? If you tell me, hey, you can't spend more than $5, and I spend exactly 5, you tell me I'm towing the line, but I haven't not met your criteria. So this is going to be our inequality. Maybe we do I don't want that to get too messy. This kind of meets our blue criteria that we underlined up there. No more than 30 feet in width. Well, my width is resembled by Y, and it's less than or equal to 30. But there's another criteria here. She wants to use at most 180 feet of chicken wire. Now, what's she using that chicken wire for? Well, we got to look back to the initial sentence. Mrs. Paulson bought the chicken wire to surround the perimeter of her rectangular garden. So what this tells me, right, if we get a little bit more practical, we know that a rectangular garden is made up of lengths and widths. And we know that with rectangles, the opposite sides are the same. Now we know that this width over here can't be more than 30 feet, and that's what the blue starred inequality resembles. But in general, she's using no more than 180 feet for this perimeter. So this whole thing cannot be more than 180 feet. Well, that means that 180, and I'm already going to go ahead and put the open side facing it because I know I can't exceed the 180, is the max we can have for making this perimeter. So what's the formula for perimeter? Well, perimeter is add up all the sides. It's the outside boundary. Well, what is our perimeter? Well, we don't have specific numbers because we don't know the length and width. But I think this is where the picture can be really helpful. We just add up all the sides to get the perimeter. So what? I've got an L, and I've got a W, and I've got an L, and I've got another W. Okay? So what this second inequality tells us is that our perimeter, the length plus the width plus the length plus the width, cannot be bigger than 180. It could equal it, again, at most. That means 180 is okay, but we can't go over it. Put a little red star here. Okay? And really now at this point, I've got a system of inequalities. Now again, what you'll notice I defaulted to, because my brain's running in lengths and widths, is I used L and W's. And you go, wait a minute, Mr. Carter, you've got a bunch of variables going on. Again, I need to pay better attention, so we all can improve at stuff. I need to pay better attention to this second sentence. X equals length and Y equals width. So all I'm going to do is I'm going to just erase this, and I'm going to replace it with Y's and X's, right? Y's for the width and X's for the length. Now we see here that we got some like terms we can combine. And so when we do that, we get 180 is greater than or equal to 2y plus 2x. And some of you might even skip this middle step. Some of you might have jumped over it and said, I already know the perimeter of a rectangle is 2y plus 2x. That's cool. So at this point, we have accomplished letter A. Let me erase maybe some of this underlining, make stuff a little clearer. We have accomplished letter A. Okay, we have written a system of inequalities. Now what we have to do for part B is we got to graph the inequalities and list at least three, that's some bad grammar, list at least three possible solutions. Okay? So to do this, okay, let's go ahead and we go, can we graph these? Well, if you remember from chapter 7, we prefer our inequalities to be in slope-intercept form when we're going to graph them. So let's ask ourselves, are these inequalities in slope-intercept form? Well, what's the hallmark of slope-intercept form? Well, y is alone. Well, I look at my first inequality, and I'm going to box it in blue because, hey, that one's good to go for graphing. Okay, we have y by itself. We don't actually have a slope for that one because we don't see a variable times our x in slope, or I'm sorry, a coefficient times the variable x in our slope-intercept form. Now, if we look at kind of our other inequality, this one is not in slope-intercept form. Let me bump it up here real quick. This one is not in slope-intercept form because y is not isolated. So what we're going to need to do is before we graph it, we're going to need to isolate that y variable. Now let me be clear here. You don't have to do this. This is technically in standard form and you can graph it that way, but you can't use those little tips and tricks we learned for graphing inequalities unless it's in slope-intercept. So I'm going to go ahead and turn this into slope-intercept form by isolating the y. And I'll start that process by minusing 2x from both sides. And then divide everything by 2. And this is really key. We've talked about this a lot. When you divide one side of the inequality by something, the entire other side has to be divided. And if you want more information on maybe why we do that, we can talk about that one-on-one, but I'm not going to dig into that in this video. And so what we end up with here is 90 minus x is greater than or equal to y. You'll notice I simplified the 2 over 2 and the 180 over 2 because they turned into nice values. And so now we have our other inequality in slope-intercept form. Okay, pause the video if you're following along because I'm going to erase it in a second. Go ahead and get that jotted down. I'm just going to rewrite it up here, a little bit nicer, a little bit cleaner. Again, I don't recommend you do this on your test, but I'm just doing it for sake of space. Okay, so we've got our inequalities. They're in slope-intercept form. They are ready to be graphed. Let's start with the blue one. Again, what we see here is we don't have a slope. Well, what that we've learned in the past, and again, we can dig more into this one-on-one if you want. I won't talk a ton about it in this video. But when we don't have a slope, or in this case, a slope of 0, it's going to produce a horizontal line. So the way we start graphing these inequalities is we always start with our boundary lines. And we notice the one in blue is going to be a horizontal line. Now I notice here my scale, traditionally we assume the scale goes up by 1, over by 1. Obviously with the values we got, that's not going to work here. So instead, I'm going to go by tens. You don't have to go by tens. You could go by maybe 20s or 30s. It's really kind of your call. I'm just personally going to go by tens. And so what I'm going to do is I'm going to go ahead and I'll do this one in blue. And I'm going to plot my y-intercept at 30. And again, as we've hit on, I don't have a slope here. So when you have a slope of 0, I shouldn't say you don't have a slope. Your slope is 0. Okay, so clarification there. When you have a slope of 0, you don't see a slope. What you are going to do is you are going to draw your line will be, your boundary line here will be horizontal. You're going to notice a couple things. Number one, you're going to notice that is a solid horizontal boundary line. This is because our inequality is an equal to. If it was not an equal to, it would be dashed. And again, we've dug into that in the past. If that doesn't make sense, you can talk to me about it one-on-one. You'll also know I'm only extending right. Okay, I'm not going left. And this goes back to kind of what our variables stand for. And it's important to remember this. X is the length and Y is the width. Not a bad idea to label these. Again, over-labeling isn't going to hurt you. And it's really important to understand that what would happen if we would go left? Well, we're getting into our negative x's then. What are our negative x's? It's negative length. We cannot have a negative length for the perimeter of our rectangular garden, okay? Or as a side of our garden. That can't happen. The lowest you could have would be a length of 0, and then you just have fence lines. So really, probably in practicality, I guess technically it could be 0, but in practicality, it probably needs to be even a little bit bigger than 0, but we certainly cannot go negative, okay? Now our next step here is we need to graph our other inequality. Well, again, I notice my y-intercept is 90, so I'll put a dot there. And then we kind of run into a problem. And you go, what's the problem? Well, before you jump straight into graphing, remember, we changed our scale here on the y-axis. This is no longer going up 1, right 1, okay? Or my scales aren't going by 1s anymore. Rather, what's happening is I'm going up by 10s, but currently I haven't changed my right scale, so we would assume we're going by 1s. Well, what's our slope for this? Well, our slope here is negative 1 over 1. That's what it means when we have a negative just in front of that x. Well, that tells me I need to go what? I need to go down 1, right 1, down 1, right 1, or up 1, left 1. Well, if I go down 1, right 1, I'm going by tens here on my y-axis. That's going to be incredibly messy because if I go down 1, right 1, I mean, even you can see with making my pen, it's nearly impossible because this would be to 89, right 1, 88, right, and it's just going to create this messy horizontal line. So we need to edit this slope a little bit to make it a little bit nicer. Well, how can we do that? Well, we can use equivalent fractions. If you remember, we simplified 180 minus 2x over 2. We simplified this 2 over 2 to be 1, but you actually can do the same thing going backwards. You just need fundamentally the fraction to turn into -1 so you don't physically change the slope. You're changing how it looks, but you're not fundamentally changing it. So here it was 2 over 2, and we turned it into 1 over 1. Well, you're used to doing that. That's simplifying. But we kind of want to unsimplify here to work with our scale. Well, look at my y-axis. I'm going by tens. So ideally, it'd be nice if I could go down by tens instead of down by ones. So instead of -1 over 1, I'd like my slope to be going down by 10. Well, in order to do that, I can't just write -10 over 1. That would change the slope. But what I can do is write it as -10 over 10. Again, it's kind of like unsimplifying. By doing that, that is still going to simplify down to -1, just like -1 over 1 does, and just like -2 over 2 does. But it's going to work a lot nicer with my scale. So we're going to kind of edit this slope. Maybe I'll rewrite this guy here. We're going to kind of edit the slope so that it works well visually with our scale. Now what that means is, again, we haven't done anything to our x scale yet. And if you look at my slope, I'm going down 10, right 10 now. So what would make sense is to go over 10 on my x-axis. And all I've done here is I've just kind of manipulated my values, not fundamentally changing the slope, but manipulated my values so we get a nice visual on our graph. I don't want to dig a ton more into that just for the sake of time in this video. I know changing the scales, changing the slope can be confusing. If you want more one-on-one help with that, if that isn't making sense, just let me know and we can work together with it. So we've changed our slope, not fundamentally, but just kind of how it looked. We've kind of unsimplified it so it worked with our scales. And now I'm going to go from my y-intercept of 90, I'm going to go down 10, right 10. And again, you can see just how much nicer and cleaner that looks. We're putting dots on nice grid lines. Again, this is going to be a solid boundary line because it's an equal to inequality. Again, if you want more information on that, as always, you can kind of talk to me. Now, final step here for our graphing. With inequality, unlike equations where your solution is just a line, okay, your equations just produce graphs that are lines, at least the ones we're working with often in Algebra 1 until we hit future sections. We know with inequalities that the solution isn't just on the line, but it can be above the line or below the line. We've talked about this in the past. So we need to do some shading. Well, the advantage of turning our inequalities into slope-intercept is that we have some tips and tricks we can use for shading. When the open side faces away from the y in slope-intercept, we know to shade below. When the open side faces the y in slope-intercept, we know to shade above. Well, both my inequalities here have the open side facing away from the y. So I know I'm going to shade below. Also, technical note here, again, you notice I didn't extend outside the first quadrant when making the boundary of my second inequality. Again, this goes back to the idea that we can't have negative lengths and widths. And you're noticing I'm doing the same with my shading. And what we have effectively done is we have now graphed the inequalities. Okay, this is, as you can notice, takes up the bulk of the work. And obviously you have to deal with changing scales. And really that's what's going to probably cause you the most problems when it comes to word problem inequalities. It's just changing scales as necessary. Now you'll notice here, and as we've talked about a lot, your double shaded region is going to be your solution set for inequalities. Okay? And I'm going to kind of outline it here in green just to make it clear. This kind of trapezoid here. Okay, this is going to be your solution area because this is where we double shaded. Okay, the area above that's only red, that's solutions that would make the red inequality true, or in the context of the problem, that meets the criteria of 180 feet of chicken wire, but doesn't meet the criteria in blue, the no more than 30 feet in width. Conversely, we've got this little blue region off to the right here where we have less than 30 feet of width, but your solutions there are not going to meet the criteria for the 180 feet of chicken wire. Here in green, though, you're going to meet both the criteria, and this is the last step. We need to write 3 possible solutions for the length and width of the garden. Well, remember, x is our length and y is our width. So we can just kind of pick some points in here. Okay, one of them could be 30-10, which means, again, I've got a length of 30 and a width of 10. Another potential solution, 50-20. Another potential solution, maybe 10-20. Okay, and what you can do is you can check these to indeed make sure they're true by plugging them not into one, but again, your solutions here have to make both inequalities true. Well, if we think about the first solution here, 30-10, does it have a width less than 30? Absolutely. Does it make this inequality true? Well, again, if we look at negative 10 over 10, which is just negative 1, times your x value of 30, you get negative 30. 90 minus 30, is that greater than or equal to 10? Yes, it is. 60 would be greater than or equal to 10. And I didn't write that out, but you could write that out on your paper. And again, you can just think about it in terms of the criteria as well initially. Again, we don't have more than 30 feet in width. And with these values, maybe it's easier to think about it like this. If we plug them into our rectangle over here, is that less than or equal to 180? Well, 10 and 30 is 40. 40 and 10 is 50. 50 and 30 is 80. Absolutely, we're below that. Okay? And really, you could pick any point in here. Okay? It doesn't matter. And again, what I would advise Mrs. Paulson to do is to pick one that suits her needs. Maybe she doesn't need a massive garden, or maybe, 10-10, well, technically a solution, maybe it might not meet her needs and she needs to do more like 60-20. It doesn't matter. Again, just for this problem, those are some potential solutions. Okay? Guys, I know I dug pretty deeply into this problem. It probably won't take you this long to solve it, but I wanted to make sure you kind of saw all the ins and outs of it. Again, if you have version 2, your problem should look almost identical. It'll be a little bit different numbers. Again, if you use different scales, your graph is probably going to look a little bit different. Doesn't necessarily mean it's wrong. Just the visual will be a little bit off. And again, final reminder, if any part of this confused you, if you're still stuck, I'm more than willing to help you one-on-one. Have a great day.